All right, welcome everyone. Very excited to introduce Kurt House. Kurt House is a PhD in physics from Harvard University. Worked for a while in the chemistry and physics of CO2, and actually started a company in that area of carbon sequestration. Realized rather quickly that renewables are a whole lot cheaper than carbon sequestration. And so he turned that now into a new big venture in critical minerals. And so Kurt has created an incredibly innovative company over the 4 years now, and I've been part of that company. It's a company that really truly uses AI and machine learning and also quantitative science as the foundation of their operation, and they have achieved something I think no mineral exploration company has ever achieved, is they are now active in 50 different assets on 44 different continents. And so how that is done and how you do all of that, it's my great pleasure to ask Kurt to present that.
Thank you, Jeff. Very nice introduction. Super glad to be here and to chat with everyone. I want to return the favor to Jeff. He's been a key collaborator for us since basically the beginning of the journey, and contributed him and his various research associates, grad students, postdocs, et cetera, have contributed meaningfully to the science that we've done and the technology that we've invented and deployed around the world. And I'll take this moment to do a plug. Oh, not advancing. Oh, there we go. Okay. Quick plug for the thing that Jeff has launched called Mineral X, which is taking his entire research group and focusing it on finding the materials of the future. And really awesome to say, if you read in the Stanford Daily today, it summarizes a talk he gave on his own personal journey away from fossil fuel funded research, because he had largely worked with oil companies and others in the past, but is now fully invested in the renewable energy future, which is really, really awesome. And so Mineral X just got started. This picture was taken in the building a month ago or so. We got Stanford folks interlaced with KoBold folks, as well as our partners at one of our major projects in Zambia, who were visiting. This is from the Zambian parastatal mining company, who were visiting to understand our research more fundamentally. We're doing a symposium in June. It's the sort of launch of Mineral X, and all students interested in this kind of stuff, I'd encourage you to reach out to Jeff or other people in his group. All right. So let's get into it. The talk is going to be kind of in sort of 3 sections. I definitely encourage questions along the way, for sure. I mean, the whole point of this is to leave this room knowing more than you came in, knowing more than you knew when you came in. So please, by all means, feel free to interrupt. I'll talk a little bit about the sort of big challenge, the big picture macro story, then quickly get into the depths of technology and deployment. And I'm going to break up that in 2 groups. Very, very broad scale. So prospecting over continental scales, 1,000, 10,000 kilometer length scales. And then we're going to narrow in deeply and talk about how we explore specific deposits at the length scale of 100 meters or so. We'll start with a little commercial.
Here among nature's vivid hues in remote northern Canada is a modern-day treasure hunt.
Courtesy of NBC News.
Do you see the future of clean energy?
Oh, for sure.
Kurt House is CEO of Cobalt Metals, and what he sees beneath this treescape are the essential elements for electric vehicle batteries.
So the key elements that we're looking for are nickel, cobalt, and copper.
To find them, KoBold uses this 1,700-pound metal detector, collecting data from nearly 1/3 of a mile below the surface and sending it to the company's California offices. There, it's transformed into what amounts to a Google map of the Earth's crust.
We're using advanced data science, machine learning, and artificial intelligence to make predictions about where underground we might find high concentrations of the key battery metals that we're trying to find.
By marrying old school field work with big tech, House believes they can increase the odds of finding mineable deposits from 1 in 100 to 1 in 5.
So if we increase the success rate, then we spend less and find more.
How much do we need to take from the earth? KoBold estimates we need $10 trillion of new discoveries of copper, nickel, cobalt, and lithium.
But the road to a cleaner future will take an environmental toll. Mining still disturbs the earth. So how is this different than taking fossil fuels from the earth?
We only have to do it once. With fossil fuels, you bring it out once, and then you burn it and you never get it back. Mining, we'll take the metal out of the ground, we'll put it into cars, and we'll recycle that metal again and again and again.
Reduce, reuse, recycle, mining the earth to sink. Here among the
Okay, it's at 10 trillion. That was about a year and a half ago. Current number based on current commodity prices is about 15 trillion. And here's how we get to that number. So look at the copper figure first. We're looking for copper, nickel, cobalt, and lithium. We call those the materials of the future for very specific reasons. Horizontal axis is time. Vertical axis is annual production. The gray wedge is current mine supply, and that includes projects that are right about to come online. And then we know with high accuracy what they are expected to produce based on their current capital investments, the current mine plan. So that's the gray wedge. We then make the most aggressive recycling assumption we can. We assume 100% of atoms are recycled in perpetuity, which is physically possible, but clearly the number is going to be a lot lower. And then the top line, the demand, is how much material you need to build a fully electrified light duty vehicle fleet globally, which is about 2.5 billion cars globally by 2050. And so the wedge is just how much more you need beyond all the other demands for these metals. And it's really interesting to kind of look at it, because in the case of something like lithium, the growth is sort of staggering, right? It's like a 30x increase in global production that you need. So that you might look at that and think that's sort of insane, but it's also the case that we're starting from a very low base, and there's been almost no historic lithium exploration efforts. Lithium became an essential and highly valued commodity in the last 10 to 15 years. Copper, maybe we're only doubling from the baseline, but that's doubling on a gigantic baseline, right? Copper market is a $150 billion market. And humans have been actively exploring for and mining copper for thousands of years. Nickel is sort of the mid case, and cobalt is more like lithium. When I first made this chart 2 years ago or whatever, numbers changed a little bit over time, but commodity price is the only thing that really changes. This was 3 trillion, not 7 trillion, and the difference was commodity prices. The lithium price has gone way up. So that's part of the story. That's half of the story, maybe the macro story. It's the second half of the story. Anyone know what Eroom's law refers to? Read it backwards.
Moore's law.
It's Moore's law backwards. Okay, so the vertical axis.
Oh,
You got it. The vertical axis, exploration effectiveness, which is number of tier 1 or tier 2 discoveries per dollar of exploration expenditure, and the vertical axis is time. And so what you see is the industry has been getting worse and worse over the last generations. In fact, down by about a factor 8 by that metric. There's other ways to look at it. Numbers change a little bit, but the fundamental trend is quite robust. So we're spending more and we're finding less, right? We're doing more and more, and we're getting worse and worse at it, right? Why is that? Any guesses? Why do you think this is? This is a fact, basically. Yeah, go for it.
all the easy stuff is already taken.
Damn, good job. Excellent guess, and I think that's right. That's a hypothesis. We don't know for sure, but that's certainly our guess, or at least maybe the first principal component. And here's support for that. So vertical axis is depth. Horizontal axis is time. Every dot there is a discovery in depth and time space. So where the centroid of the deposit was and when it was discovered. And we've got four ore types that we're actively searching for, right? So these are basically all the major discoveries in these commodities throughout the last 100 or so years. And you see they burst virtually all at the surface. They're virtually all right at the surface. They were directly detectable at the surface, meaning you could see them in an outcrop. If you were a skilled geologist, you could identify ore minerals, or you can measure a highly elevated concentration of the element in a soil or regolith sample, right? But directly detectable. Even you might look at cases like this and say, oh, well, mostly at the surface, but they found some things at depth back in the 60s. Those are the exceptions that prove the rule. This is a Jinchuan 2, and this is Jinchuan 1, right? So it was found after the surface discovery was made, it was mined, and then at the bottom of the pit, they discovered a new but related ore body. It was like a sister body. Very recently, you've gotten some true blind discoveries, but that's the major problem. Now you might look at this and I think reasonably ask the question, well, maybe these things form at the surface. Maybe like that's why they're all there. That would be a reasonable question to ask. We know certainly for these ore systems, that's not the case. These all form in reducing environments. In the case of lithium pegmatites, for example, we know they form at the depth interval of 10 to 20 kilometers deep. And it's only through post-formation tectonics and erosion that actually exposes them at all. So that's kind of good news, right? If you take a cross-section of the Earth's crust at any depth, you'd actually expect the areal density to increase as you descend through the crust. So we kind of know there's lots of stuff out there to find. They're just way harder, right? Way harder to find. So that's the challenge. And when you marry this and this, right, we have a gigantic challenge. So KoBold today, Jeff referred to it briefly, about 4 years old. We are operating on 3 continents, 4 if you consider Greenland a part of Europe, or 3 if you consider it a part of North America geologically. We have people on 4 continents. We have about 50 properties. I'm going to be giving examples from a project in Australia, a project in sub-Saharan Africa, and a project in North America. So we're going to jump to Zambia, probably our most important jurisdiction currently. This is a drone shot from a deposit that we're developing there. We made kind of big news in December when we announced this very large investment. This road we built over the last several months. Here is us making this announcement in Washington, D.C. at the African Leaders Forum. That's my co-founder, Josh Goldman. That's the U.S. Secretary of Commerce. That's the president of Zambia. We're quite proud of that. And now we're off and running. We have, this is it's not a live feed, it's a time-lapse feed, but it's over the last couple days. We have two drill rigs on site right now, and we'll have 5 in the next couple months. So we're in the middle of a really dramatic ramp there, and it's quite exciting. It's one of the neatest new copper deposits around. Sorry. Okay, now let's get into the science. So the title of the talk is Bayesian exploration, or that was subtitle or something. We use that phrase a lot. What does it mean? Well, basically it means we try to stick to Bayesian statistics. I'm sure most people in this room know what I'm talking about. The principal difference between Bayesian statistics and frequentist or standard statistics is the construction of a prior, right? But that is, and of course, it's easy to say and very hard to formally come up with a prior estimate of your knowledge about something and then collect and then incorporate new information and come up with a posterior. But it's kind of immediately evident how valuable this would be in the exploration business, because fundamentally the exploration business is an information problem, right? If you knew if God gave you a perfect map of the Earth's crust where you knew where every atom was and the form of every atom, you'd be a perfect explorer. You'd also be a perfect miner too, right? Because you know exactly how to optimally develop a deposit. We don't have that. We have a huge amount of uncertainty, very, very sparse data problem. And so this is a very different information problem than most companies in Silicon Valley deal with, right? Most companies in Silicon Valley, like sort of canonical example, a social media company or something, it's getting an avalanche of information thrown at them at really negative cost. And then they develop data science tools that sort of sift through the avalanche to find subtle signals in the noise. Here's a very, very different problem. We have a huge sparsity of information, a gigantic amount of uncertainty. And our aim, and not only a giant amount of uncertainty and sparse data, but a very high marginal cost of new information, right? New information means we fly that helicopter around with that big metal detector, or we drill a hole somewhere, or we do a surface geophysical survey out in a remote location. It costs a lot. So a very high a marginal cost of information means that the key decision is what is the next thing I'm going to do in this exploration program to decrease my uncertainty the most, right? And to being able to formalize that is really hard and really important. And so in this example, right, imagine you have some prior estimate of some measurable, kilograms of metal in the ground at a particular location, whatever. And then, imagine you know what the measurement result will be, but you can constrain how much it will reduce your uncertainty of various measurements to take, right? So you can take measurement 1, measurement 2, measurement 3, measurement n, whatever. Very different things. Could be a different type of measurement. You could be taking geochemical samples versus measuring a gravitational signal or whatever. But you have imagine you were able to constrain the reduction in uncertainty. Which is the measurement you should definitely not take? Yes, measurement 2. You don't learn anything, right? You get the exact same, their posterior is identical to the prior, right? Which would be the best measurement to take? 3. Yeah, you get the greatest reduction in uncertainty. So we formalized this with Jeff and others. You can read the paper. There's lots of fancy math and Greek letters, but that's basically what it comes down to, right? And I think this 2 sentences here say it really well. It quantifies by how much, on average, it is EOI, efficacy of information. I'm going to use that phrase a lot. EOI quantifies by how much, on average, future information reduces uncertainty on some discrete property of interest. Okay, so now let's talk about some examples. Now we're talking about large-scale prospecting. Continental scale. Okay. To start, I'm going to give a very, very quick primer in a particular ore type because it'll be useful for everything that goes on beyond here. We're talking about what we call magmatic nickel sulfides. So this is magma has come up through some conduit in the Earth's crust. It's usually ultramafic or mafic, so high in magnesium, high in transition metals, relatively lower in silica or aluminum composition. Comes up through the Earth's crust and interacts with some source of sulfur, usually in sediments. Sulfur, it turns out, is very, very good. It forms an immiscible melt within the magma. And it's good at scavenging transition metals out of it. So you concentrate the nickel, the cobalt, the platinum group elements out in much higher concentration of metal sulfides. You can get a factor of 100 increase in concentration. And so what these things look, when you find them, they often look like they sort of have this kind of champagne glass kind of structure because the magma was squeezing through and then it finally got to the near surface and kind of spread out. And a place where we often find the richest concentration of sulfides is in the keel. Think of like a sailboat keel. That's a sort of observational. There's good explanations as to why, but sort of just have that in your mind. And a couple of the things to understand is that ultramafic rock tends to be, so the whole collection of frozen magma tends to have a high magnetic susceptibility, and the high meaning high contrast with the sediment or whatever it froze within. And then the actual ore minerals, the stuff that you'll mine, tend to have a high conductivity. sulfides, massive sulfides in particular, very, very conductive relative to things around it. So that's important, right? So now we have physical, petrophysical contrast between the stuff around it. We can use that in principle to detect these things without indirectly. Okay. So with that in mind, one thing that would be great to know, so imagine the green is the top of your mafic intrusion, frozen. It'd be great to know where all of those were sticking out of the ground. Now, contrary to what I had just mentioned, the Earth is not perfectly mapped geologically by any means. A small fraction is actually mapped in high detail. So yes, the easy things have largely been found, but we think there's a huge amount of benefit in just knowing with high fidelity where these ultramafic intrusions are. Okay, so here we're in Western Australia. This is, you can see the insert up there. Here's the length scale, that's 200 kilometers. Now we're over a really, really large area, okay? And what we're gonna use machine learning and, to map in very high resolution, down to the sort of meter length scale, all of the mafic intrusions. Most of those will not have rich metal sulfides in them because they will not have had the secondary effects of interacting with sulfur and all the rest. But it's a necessary place to start. Okay, on this, I've got a small subset of the area labeled as a known outcrop or known non-outcrop. These are places with really good geologic descriptions. People, not our people, could be our people, in this instance is not. Historically, I've stood on them, they've described them really well. Maybe they've made measurements, geochemical measurements, et cetera. We have a high degree of confidence that we know those are mafic outcrops or not mafic outcrops, other outcrops, or not non-outcrops. Okay. And that's what they kind of look like if you look deep in. It's hard to tell from satellite imagery, but we have other secondary information that gives us high confidence. Curating training sets like this is really, really hard, right? And like, it's mostly known now, it's not always known. The machine learning component of it, the actual running of ML models, that's a commodity, that's trivial, actually. What's really hard is putting together these data sets. If any grad students are annoyed that they're spending lots and lots of time assembling raw data sets, you're doing the real value. That's actually valuable. Running the correlation models is not hard. So we put together that training set. Then we have lots of independent variables that we can assemble. So there's spectral imagery from satellites or planes. There's magnetics. In a place like Australia, the government and private companies have flown magnetic surveys measuring the Earth's magnetic field in a particular location. And from that is not, you can derive anomalies, things that would not be predicted by just the Earth's magnetic field alone. It changes from place to place because of the magnetic properties in the rocks in the near surface. Radiometrics, rocks are decaying and sending up various decay products. Electromagnetics, active and passive. This tells you something about the conductivity of the subsurface. Gravity tells you something about the density contrasts, the density variation. Induced polarity will tell you about induction, inductive properties. There's legacy geologic maps, which are used as sort of imperfect independent variables. And of course, all manner of geochemistry. But once you assemble that, and the really hard part, which is the labeled outcrops, well, they're both hard. This is expensive to collect or assemble. This is very hard to manually put together. Then you put it into a predictive model. That's the easy part. And then you make a prediction. So the model I'm going to show you is a two-part prediction. It starts by just telling me this is an outcrop or this isn't an outcrop. It does not tell me the composition of that outcrop. Okay. So anything that's not black on this, the model is saying is undercover, under soil, sand, regolith. Bedrock is not exposed at the surface. Okay. We have to use other techniques to investigate what's underground. But so you see, it's something like 20% of the area or something is estimated as sticking out of the ground. And this is at a meter scale resolution, far higher resolution than any legacy geologic map. But now we say, okay, of those outcrops, I want you to classify them. Tell me what the composition is. And so we've got 6 classifiers here, which are basically degree of massificity, which means on a spectrum between aluminum and silicon rich to iron and magnesium rich. So these are just words to sort of give you some sense as to where you are along that spectrum. You see there's a lot of richness here, right? So any place that's purple, right, or orange starts to be really, really interesting to us. As a place where there could be and then we cross-check, was that mapped correctly in the past, in which case maybe it's been explored? Was it mapped incorrectly in the past, in which case maybe it wasn't explored? It just has a cool example. So we'll zoom into a known case called the Money deposit. So this is an undeveloped nickel deposit. We know it's been well studied. We know the nickel's there. Probably be a mine someday. It was not in the training set that I showed you, so we can see what it looks like with just raw satellite imagery. Kind of the whole area looks sort of like this. Very, very hard to tell even what's outcrops, let alone what the composition is. But then we apply. Remember, this is way zoomed in, right? You can see it's just this tiny. In fact, actually, it's smaller than that dot. I just had to make it that way so that you could see it. That's 300 kilometers. And then down here, that's just 1 kilometer. So we've zoomed way in. And you see the richness of the map on the right, and it really pops out, right? You have a lot of mafic and ultramafic material. In fact, when you have these gradients in maficity, that's another order of strong indication that you had what we call differentiation, which is the magma was changed through chemical reactions with other stuff. So this looks really, really interesting. And of course, actually, we know that underneath there is an undeveloped nickel deposit. But that's the kind of thing that jumps out at us as being a place that would be interesting. So here's some examples of things we have found that were unknown. Well, actually, it's a blend. So we're in another very small area. Here was a true positive, and that the model said it was ultramafic. It was well mapped as an ultramafic outcrop, but there's an uneconomic amount of metal there. The one up here, also a true positive, and that it's correct. The model correctly predicted it. It had been previously well mapped, and there's a possibly economic deposit there, studied by others. So that's really encouraging. But then there's a couple cool things in here. Yeah, we've got hundreds of these, right, which are not incorrectly mapped historically or not mapped, that have a very, very similar signal to what we should be seeing for to satisfy the hypothesis that you have a differentiated ultramafic intrusion there. So those are places that we acquire through staking and then go and explore. So how good formally are these? I've shown you some anecdotes of the models doing really well, but really, how good are they? Well, we can show you rigorously. So this is through model performance or cross-validation techniques. So here's this area. Keep in mind how gigantic it is, right? Just so this is larger than the state of California. We randomly collect, in this case, squares that get left out of the training set. Okay, so imagine take CV group, cross-validation group 0. That's the red here. So the computer randomly Swiss cheesed and pulled all those areas out. So we trained the model on everything else, not on what was in there, and then predicted within those, right? And then we have labeled training data inside those that we can compare it against, right? Standard cross-validation. And so here is what the results look like. So this is a precision recall curve. These are relatively straightforward. Recall is the horizontal. This is the percentage of true positives that you identified correctly. Okay, so if you got every single true positive that you knew was true, your held out case, you'd have a 100% recall. And then the precision is of those that you said were positive, what fraction actually were positive, right? And so if every time you said this is a mafic intrusion, if you were right for the held out data, you'd have a 1.0. So a perfect model would be up in the right hand corner. Why is it a curve? It's a curve because because the model gives you a probability out, and so you have to then decide, well, what probability are you going to call? Are you going to designate as the class, right? And so if you think about that, you could game this on either axis, but you can't game it on both, right? I could say, well, look, everything out there is an ultramafic intrusion. Well, then I am guaranteed to identify every ultramafic intrusion out there. I'd have a recall of 1, and I'd have a horrible false positive rate, right? So I'd be like here on the curve, right? Whereas I could do the opposite. I could say, nothing out there is an ultramafic intrusion. And if I did that, then I wouldn't get anything wrong, but I wouldn't have found any, right? So I'd be like, I'd be really low recall and really high precision. So these models, being almost square waves, are crazy good, like crazy good. And the mean performance of all the cross validation, that's the black curve, right? It means we can basically have a recall of 90% and a precision of almost 90%. So we can, if this generalized, which we have no reason to think it doesn't at this stage, I correctly identify 90% of the cases and 90% of the cases that are out there, and we'll be right 90% of the time, which is really, really good. All right. We're going to fly from Australia to Quebec, and I'm going to show how we use the same kind of concept, but now in a dynamic way with people actually in the field. So northern Quebec, 61 degrees latitude, super remote. There's snow on the ground 9 months a year, right? Everything you do, you fly in, very expensive, right? That's important. Legacy geologic maps had indicated this region that I'm showing as not prospective basaltic outflow, not prospective for the kinds of ore system that we're talking about. Okay, but we had a model very similar to the one we just showed you that indicated, actually, this is really interesting area. This is the area you want to be in. So it's models like this that led us to stake the land, and we have about 1,000 square kilometers up there. This is what it looks like up there. Internships, anyone? This is super cool and super rugged, super remote, helicopter supported. We own, think about it, we own 1,000 square kilometers, 200,000 acres, right? And we have less than 3 months up there. This is what I mean by exploration being an information problem. And the key information problem, the key nature of the problem is, what information do I need to collect next, right? That is the problem, because I can't, should I sample here or there or wherever there? I can't sample them all. I can sample some fraction of it. I take measurements of some fraction of it, whether it's geophysical or geochemical or whatever I'm looking at. I have a very limited space, very limited fraction of the available measurement space I can actually measure. Okay, and that's critical and super hard. Our first season here, our team collected and took out 5,000 kilograms, 5 tons of samples. Getting 5,000 kilograms of samples out of there is a logistic, feat. Right? It's also a de minimis fraction of the material that's up there, right? You got to make sure you get the right 5,000. And so how do you do that? So this gets to the efficacy of information problem, this whole idea of collecting the right information, the right types of information, and or the right locations. So here's that initial model that I showed you. Okay. These models, they're better than just predicting what the stuff is. They also quantify the uncertainty, right? So here's the uncertainty of that initial model. Okay, so every pixel up here, this in this case, it's a 3-class model. You earlier saw 6-class model. It doesn't matter. The point is, every pixel has, in this case, 3 probabilities associated. Probability of being class 1, class 2, or class 3. And you could easily add a 4th class. It's an other or whatever. Doesn't matter. If a pixel says, class 3 model, it says 1/3 probability X, 1/3 probability Y, 1/3 probability Z. Well, the model knows nothing. It's saying equally good any of these things. I have no idea. That's a very high uncertainty, very high entropy location. If another one is like 98% thing A and 1% thing B or thing C, then the model is very, very confident. The model might be wrong, but if you're confident in the model, you say, okay, well, I know that location. That's a low value information That's low value information. High value information is places where I have a huge uncertainty, where the model doesn't know. So if I take a low confidence training point or a low confidence prediction and I pin it into a high confidence training point, then I make the model, the impact on the predictive power of the model is very dramatic, right? So that's a better spend of exploration dollars. So what we do is we visited this area and set up 4 field stations, which are just basically places where we're making a bunch of in situ measurements and observations, taking samples. Okay, so just 4, guided mostly by the high uncertainty. And then you rerun the models. Doesn't this look like it's a higher resolution image? Not. Same exact number of pixels in this figure as in this figure.
Has less brown.
It looks sharper. It is sharper. It's because the colors aren't blending into each other, because the probabilities, because the model is more confident that it's found, that it's determined what the material actually is. And the things actually are kind of coherently forming geologic bodies. And then we can quantify the uncertainty, and you can just see, remember, yellow is high uncertainty, purple is low uncertainty, model's way more confident. And we did that through this very, very levered way of collecting the information that was most confounding the models, right? We figured that out. We answered those questions. And we can actually quantify how well it did, both against the legacy geologic map and against its own first prediction. Again, we've got a precision recall curve. This X is the legacy geologic map. It's an X because it's just a map. It just tells you this thing is composition X, this thing is composition Y, et cetera, et cetera. We collect tens of thousands of data points. We evaluate how well that map predicted what the stuff actually was. And it did okay, right? It was something like a 40% recall and a 50% precision. Here's our day 1 model, which had about a 50% reduction in false positives and a 33% reduction in false negatives relative to the legacy geologic map. So that's good. We're doing better. We're doing better from day 1. But because we can be very levered in how we improve our models, we get crazy good by day 30, out of control good, right? So that's efficacy of information. The information that took your curve from the orange to the blue, just 4 measurements or four sets of measurements, right? Dramatically improve the predictive power of our models. All right. You on time, okay. Clock work. 12:39. Good. Okay, so that led to the discovery of dozens of mineral occurrences that were previously unmapped, which then led to a series of drilling campaigns and much more sort of advanced exploration programs. And so now this is one of our most significant programs. We're just going to spend many millions of dollars there this year. This is cool. This is a previously unmapped outcrop, and see the native copper sticking out. So it's a big chunk of copper sulfide, so chock full of copper that it actually precipitated out. So now we're going to narrow the length scale a lot. And we're going to talk about how we go after, once we find something where all the geochemistry was correct, how we to figure out if it's an economic deposit, and then how to mine it from there. So back to Australia, not that it really matters. So this is a total magnetic intensity map. So we've flown magnetic surveys, interpolated them, and you can see this kind of weird dot, this sort of blue dot, which is actually extreme magnetic. It's a reverse magnetic anomaly, meaning that it's the magnetic material froze in a time when the Earth's magnetic field was pointing the opposite direction. So that gives you some sense as to when it happened in Earth history, or at least gives you a clue. But it's a screaming big anomaly in terms of the absolute value. Okay. So what do we have? We have measurements of the Earth's magnetic field above it that say there's this gigantic magnetic anomaly. We want to turn that into an understanding of the subsurface, the bulk of the magnetic properties below it that are giving us that signal. Okay, here's what we don't do. What we don't do is candidly industry standard, which is to take that signal and come up with a single voxelized cube of the subsurface that tells us exactly what the magnetic properties are everywhere. The reason we don't do that is because this is a horrendously degenerate problem, horrendously non-unique. Okay, let's get into what that means. So you have order for a model of this scale, industry standard, we have order 1,000, even 10,000 parameters per measurement, per piece of data. Think of trying to solve, 10 equations and 20 unknowns. That's pretty hard. That's like 10,000 equations, 10,000 unknowns in one equation, right? It's totally hopeless. Totally hopeless that you could actually constrain it. But what people do is they make up an answer that's kind of fits their intuition. That's bad. The compute is actually intense, and you only get a single realization that is just hopelessly unconstrained. Literally order $10,000 per realization. You don't quantify uncertainty because you just have your one case that your geophysicist said was the right answer. Does not include prior. So only, in other words, it's deterministic only on the information that you've given it through the survey itself. Gets hopelessly trapped in local minima because there's so many parameters and so few constraints. And it answers irrelevant questions. It tells you what the magnetic susceptibility is way down here. But I don't care. I want to know what the properties of the geologic body that are giving me this dramatic response are. So what do? We do something very, very different. Something we developed in large collaboration with Jeff and his team. So we start by parameterizing a geologic body. Okay, and we do this by bringing in all of our prior knowledge about what type of geologic body this could be based on a hypothesis, right? So it's not a fact, it's just hypothesis. And so we come up with all kinds of geometric shapes that are consistent with our understanding of the physics of how these things would form, and actually have a relatively small number of parameters. A good example, this is showing an asymmetric ellipsoid, which turns out only has 13 parameters, and you can do a lot of things with that. It can become a pancake, it can become a balloon, it can become really, really weird shapes with only 13 parameters. We then, for whatever, I mean, it could be a 20 parameter model, whatever, 100 parameter model, but it's not a million parameter model, which the others are. We then generate prior distributions for the properties of that, for all the parameters. So if we have a 13 parameter model, we generate a prior of what those parameters could be. Okay. There's a lot of science that goes into this, a lot of judgment based on understanding. Then it's easy. Then we just use Maxwell's equations to forward simulate what the signal would be, what the geophysical signal would be based on every case in the prior. Okay. Then compare that to the actual measurement and all kinds of error measurements, but just figure out what's a good match and what's a bad match, right? This is cool. Actually, hold on. This part's really cool. So up until the full physics is computationally intensive, right? And so it might take, you have to do order 10 to the third, 10 to the fourth forward simulations per parameter. So if you have a 10 parameter model, maybe that's 100,000 simulations. Relatively intensive. Might take us, in an Amazon cloud, it might take us half a day or something like that. But then, once we have a good basis of forward simulations, we can train a neural net to predict what the full physics model would have said in terms of the error that it gives relative to the actual measurements would have said. As long as you've appropriately spanned the parameter space with your full physics, this will fill in the details really well, and then it is blazing fast, blazing fast. Like on a laptop, I can do like 10,000 in a second, right? So we can literally at this point do billions of simulations, and it is representing the physics, and we all kinds of ways to make sure that the physics are being appropriately represented. We then have to quantify basically what it means to be a good fit, right? So you have and the details don't matter that much. There's a lot of judgment here, but there's a lot of hard work in here. But basically think about it as a big mismatch is bad and a small mismatch is good, and sort of, you know, rank those in different ways. But once you do, then you determine the set of parameters, the posterior, which is the set of parameters that are consistent with your data, right? Of the full parameter space. So you rigorously sample it. So what does this look like in practice? Okay, so you remember that screaming reverse polarity anomaly that we saw in Western Australia. This is showing you a bunch of parameterized simulations of an intrusive-like body with various cylinders or ellipsoids and spheres, kind of, you know, like a sphere plus an ellipsoid, etc. Every one that it's showing you is an excellent match to the data. And they're very different, right? Very, very different solutions. But that's the point. We know this. We know this is degenerate. We know it's non-unique. So the game is just to figure out all the classes of simulation, the classes of models that work and the classes of models that don't work. That's the best you can do. We think that's the best you can do. And it's light years better than a deterministic inversion. Obviously, it depends on the model being a decent model, and that's hard, right? But actually, when you look at what the shapes of these things really are, it doesn't matter that much if it's a tube or an ellipsoid. We can show that the sort of error within the measurement itself is kind of in that noise. So then, okay, so you've got tens of thousands of simulations that work of models that fit the data. You have billions that don't, but you have tens of thousands that do. Okay, so what do you do next? Well, what's happening here is I'm doing the same thing I was doing in the last chart, showing these solutions that work, but then it's leaving a ghost image of the solution by adding more. Okay, and the contour chart now is the probability. So what the contour is the probability that you would hit highly magnetic susceptible material at a particular space based on how many different solutions fit the problem, the fraction of solutions that fit the problem. Basically, the assertion is the more, an overlapping location, a location that fits every single model is going to be better than a location that fits 1 out of 10,000 models. Right, that's the assertion, and I think it's a valid assertion. Okay, so we can take this, and so then we can use efficacy of information to figure out the most useful figure. The most useful. Here's my charging. Grab my mic. No, it's right here. Never mind. It's okay, right? We're fine on time, but just don't want to lose power right in the last minute.
Dr. House, did you want to close that little pop-up?
No.
Right now.
Good. Okay. So when I have these, this is the end result. We call this a point cloud, right? Every point is a probability. It's a probability that if you grabbed that chunk of material, it would be the anomalously high magnetic property material. Okay. And so you see there's certain areas that are very high, very likely to be that, other areas that are very unlikely, and the other areas that are in the middle. Now, this is an undercover. This is not outcropping. There's no evidence of outcrop. So we have to drill to figure out what it is. And you can immediately imagine picking the optimal drill hole that not only will have the highest likelihood of hitting the stuff you're interested in understanding, but will stay in the hypothesized intrusion for the longest, right? Will get you the most possible information. So you've got X, Y, and then you've got 2 angles, right? Dip and azimuth, to figure out the trajectory of a hole that will give you the most possible information. And so there's another way to see that. So imagine, okay, I've got all these, here's our prior, right? And I've got all these solutions that fit the data, and then I could just drill, I could drill a bunch of different places. I could drill off to the flank. Well, that's going to intercept 2 of the holes, or off to this flank, that'll intercept 2. In this case, if I drill along that trajectory, it gets nearly all of them. Okay, and that is the one that decreases your uncertainty the most. That's the highest EOI. By the way, it's frequently not nearly as obvious as like drill in the center, believe it or not. It's really, sometimes it's really counterintuitive. So that's the same thing. And you can see what these numbers are. Those numbers are how much of a highly magnetic material you're expected to intercept, right? So we can optimize for different things here. We could say, I just want to know for certain that I'll hit something to figure out what the heck that material is. Or I could say, no, I want to have the longest possible interval or some combination of both. There's a bit of a judgment call there, but whatever objective function you set, we can optimize it. Okay, and here's the result. So here's the result in terms of the best possible. Oh, this is a really cool figure. It's got a lot of information on it. So the size or the color of the dot tells you the P50 interval length, and then the size tells you the probability of intersecting anything at all. And so if you're down in this area, you have a high probability of hitting the thing and staying in it for a long time. And that turns out to be the optimal hole, which we're drilling in about a quarter or so. So maybe I'll come back and tell you the results. Okay, so do I have a? Yeah, I got time for it. But one last vignette. This is the same idea, but a different data type. Now we're talking about, that was magnetic anomaly. Now we're talking about an active EM survey. Okay, so an active EM survey, that's what you saw in the NBC video. A big loop, we charge it up with current. That current sets out, we turn off the current, an EM wave travels through the subsurface, generates eddy currents in the subsurface. Those eddy currents decay, right? And if they're in resistive material, they decay quickly. If they're in conductive material, they decay slowly. And you listen for the EM echo back on the surface. And then so then what you get, the raw data is this: at every location, you get time versus magnetic flux in three directions, B field in the X, Y, and Z directions. So you have for every location, you have 3 of those time series. Okay. And so you can invert this to find out not the magnetic properties of the rocks, but the conductivity, the conductive properties of the rocks, right? Same thing. We do not do deterministic inversions. We do Bayesian probabilistic inversions. Same recipe, just different data type. Here's an example of a late time. So this is the B field that you'd be seeing something like almost a second after you turned off the survey, and you see this sort of gigantic signal over here. If the material is conductive, it's gonna maintain current for a long time. So you'd expect that the late time signal gives you a sense as to where the most conductive material is, right? So that's very intriguing. So how do we do this in a Bayesian way? Well, we start with a prior without knowing anything about the EM data. We say where could the deposits be based on prior information about sort of geologic constraints, where the intrusion is as opposed to where the sediments are or something else. Okay, so we grab a whole bunch of spheres or ellipsoids, and we sort of organize them all in places they could be, and then you can easily see what this would look like in a joint distribution. So I've simplified it here just to be spheres. So you have 5 parameters now. You have X, Y, and Z of the centroid of the sphere, conductivity of the sphere, single, one value, and then radius of the sphere. Okay. And a prior is basically saying, I don't know. It's like, it could be anything within those bounds, right? Uniform distribution within those bounds. But then you compare it to the EM data and say, well, actually, a lot of those do not match the data at all. So they do not work as possible solutions. These do. We have narrowed the distribution a lot by that EM. Still huge uncertainty. You can just sort of see it pictorially in the top. You've gone from, whatever, tens of thousands to hundreds of possible solutions. But then before you drill anything, you can say, I want to drill the hole that intersects the most possible number of solutions, because that will decrease my prior the most. That will have the highest efficacy of information. And you can see what that looks like for this particular drill trajectory. The widths of the distributions massively decrease. And I'll show you a cool example. This is a real case. So solution said lots of possible solutions, orientations, but what was clear is this one trajectory intersected almost all of them for about 100 meter length scale. Okay, so that's the information I want to know next. You know, so I want to drill this hole. Really, I want to know what the material is, what the petrophysical properties of the material are along that trajectory. And so here's the initial prediction. So this is depth now on the horizontal, lateral conductivity on those one of the vectors of conductivity on the vertical. Okay, and now we start drilling, and we expect very, very little. And we're basically saying none of the material is conductive at all until you get to that conductive piece. Now, obviously it has some conductive value, but it's order of magnitude higher, right? It's 4 orders of magnitude more conductive. So for all intent and purpose, we're just saying it's just one conductor in a vacuum down there. And sure enough, nothing, very little, very little. Whoa! There it is. Oh. And so we nailed it. We totally nailed it. And there was an incredible conductor, basically a set of conductors right along that interval. And you'll see that we actually predicted uniform high conductivity across that interval. But we knew that was wrong. And I'm not sort of bragging here. We knew that was wrong. That was a limitation of the model. We had used a parameterization that had uniform conductivity within the body, right? So we were saying, okay, we know this interval will have really high conductivity, horizontal conductivity at various lengths. It could be continuous to the whole thing. It could be just spots. We'll get the same signal. That would fit the data. We could have had a more complicated model and actually piece that out. But the key is we got exactly what we were predicting. And so we've done, we just solved the world now. And at this stage, we have a higher or more than 85% technical success rate on drilling. So this is a nickel sulfide chunk right here, massive sulfide of nickel sulfide, copper sulfide. This is a really nice disseminated sulfide material. So these are the ore minerals that are gonna power your next electric car. And that concludes my remarks.
I think one more thing I wanted to say before going to questions is that what Kurt has really also done in his team is that people educate themselves. And now there's a lot of physicists understand that when geologists say rock, it can mean a million different meanings. That's one of the contributions, as you see, you're a great geologist. So any questions from students? Yes, in the back there.
Do that scale model. And I just imagine it's so much, like if you're going pixel by pixel, you have
Yeah. Fantastic question. We're this constrained. We're not compute constrained. There's my credit cards. Yeah. So I mean, yes, in a sense we are. We all of this is done in the cloud. It's all done. We use AWS. Our compute right now is actually a relatively small fraction of our overall budget. You can run a lot of AWS servers for how many helicopters you can fly, things like that. But nonetheless, we are. And here's an area where we're really constrained is memory, actually, right? Because the biggest EC2 box you can get on Amazon has whatever, a few terabytes of RAM, which is a big box. But that becomes very limiting. That's all the information it can hold for so any particular matrix inversion has an absolute upper limit. To the degree to which things are, very parallelizable, and any of the physics simulations are like totally parallelizable. So your intuition was kind of spot on. Like we're actually really not limited in our geophysical inversion work, stuff I was showing. We're more limited in exactly as you said, the very large scale ML predictions because of memory, not cycles, but in storage memory. So we have a big software engineering team that works along with our data scientists and geoscientists, and they've done very clever things about what you'd imagine, sort of tiling up, taking the big images and breaking them down into smaller ones. But then you have edge effects, you have to do overlapping images, and there's a lot of that work. So very good question. Yeah.
So at the beginning of the video, I just put up all the economical success of exploration and then we said that it was 1.5 Or the work that you have done, like already the ideas of this or this. What is already playing out that you.
Yeah, super good question. So you're spot on that 1 in 5 is like that's our objective, right? And we will know that we have definitively hit that with large number statistics sometime in the next 10 years. Right, so that is definitely an objective now. We've set the objective because we think it's attainable. It means we're going to fail 4 out of 5 times. Probably a better way to think of it actually is because it's like what even is a trial? If I look at a map and then do some quick calculation to decide not to pursue something, does that count in my denominator or not? Right, and so a better way is just how much money you spend per discovery. And the industry is about 2 to 3 billion, and we're aiming for 100 million. That's per major discovery, right? That's what we're aiming, and I guess say we're on track for that.
Can you talk a little bit of the Zambia project maybe? Because that's like more of a brownfield.
Yeah. Well, it's brownfield because the hard part's been done. So yeah, we've largely defined what the body there. So it's a very different ore system than I was talking about here. I was talking about magmatic nickel sulfide deposits, which have this very strong physical contrast in the various measures we were looking at. That one it's in a sedimentary basin, totally different kind of ore system where the ore fluids, the copper or the cobalt was dissolved in hydrothermal fluids, water, hot salty water, that then had some change in pressure, temperature, pH, reductive capacity, change the phase diagram such that a bunch of the ore minerals precipitate out in particular locations. And so we have a bunch of projects in Zambia. We have 4 or 5, like maybe 6 even, I can't remember. We have a bunch of projects in Zambia. One of them is much more advanced. So that project is really in the phase of pushing it toward a full engineering feasibility for the mine development and ultimately mining. We expect to be mining there within the decade.
Adrian?
This is more like, I'm guessing the weeds, or when you showed the model validation and you had the different training data sets, there was one that fit really poorly and or not.
You're very astute.
And I was just curious, yeah.
They took my class and they versus recall. Well done, yay.
Super astute. Yeah, so CV group 3. So it's actually not really poor. It's just much less good than the others for sure. So what? Take a guess. What do you think's going on?
Well, that's what I was wondering, because if it's pulling random points, I was just curious, like, does that happen? Do you see things like that relatively often?
Yeah, so what is happening here is that not all training points are created equal, right? There are training points that are more important for determining the predictive power of a model than others. And so you sort of have if you imagine a value per training point, it's actually, it can be quite heterogeneous. You have certain training points that end up being really important. And so I can't remember the total number of training points or the total number in each cross-validation group, but it turned out, and we didn't actually know this, so this is one of the reasons to do this stuff, is it turned out that a subset of the really valuable, a disproportionate number of the really valuable points happened to be in CV group 3, right? So when we did this version of cross-validation, that the model trained on everything that didn't include those handful of really valuable points, which is a less good model, right? And what's interesting is that it's sufficiently heterogeneous that if you do it again, if you scramble it again, to your question, I haven't actually tried this on this particular one, but I would bet that you'll see a similar thing. If you scramble up, you'll see a similar thing, because all it would take is 4 or 5, half dozen really valuable training points to be sort of co-located in some area, and then those are going to always be in some left out in some cross-validation group.
You almost use that as hone in on.
Yeah, for sure, absolutely. Then you say, okay, what is it? Let's add back training points to CV group and see. And sometimes it could be a single training point that will end up moving the curve up kind of materially. And there's then you ask a whole bunch of questions. Why is that? Like why? And these are tree models, I think. So why are the trees branching so much on, on that particular data set, right? Those are great, like results like this are actually great ways to interrogate the models.
We'll take one more.
Yeah, it was great to see that both scale and like a very continental scale and narrowing down to like a single mine scale. And you mentioned that for the broad scale, the challenge is not necessarily like doing a machine learning, but compilation of the data. And it seems like you have a pretty innovative way in both ways to like process whatever you want. But we're kind of curious, what are the kind of technical challenges then? What are the future technology that you want? Like, what are the given kind of the challenges to, I don't know, really proceed like whatever the goal, like 1 in 5, to accomplish that? Kind of, where do you see?
That's how long do you have? That's a super good question. I'll try to maybe address it over lunch with the students more fulsomely, whoever has lunch, but I'll try to quickly get some highlights now. So, I mean, one of the things is we are probably, I would be surprised if we're currently working with 5% of the available data. We are, and we're using way more of it than anyone else for sure. But there's just ocean. Humans have been collecting information about the physics and chemistry of the Earth's crust for millennia in some sense, and certainly in the last 100 years to rather sophisticated degrees. And the Earth's crust changes very slowly, right? As long as the data was collected in fidelity, it's likely to be useful. But it's horrendously distributed, horrendously organized, right? It's stashed in academic papers. Sometimes they're digitized, sometimes they're not. Old geologic reports. Every single jurisdiction has a different way of husbanding, of archiving and making available data. The slide I didn't show here was this project we have in Zambia to digitize all of their legacy information, which is just warehouses of information. So probably there's kind of no shortcuts there, right? Like once we have all the information, we kind of know what to do with it. But it's an extremely expensive in sort of in money, but more in just time and opportunity cost of human power to actually identify, digitize, and then structure. There's a whole software engineering challenge. How do you structure those various legacy data types in ways that can be universally interrogated by humans and computers, right? We are, like I said, we are in the first mile of a marathon there for sure.
Thanks, Kurt. Zoom. Then I can ask them to mute.
I'll make sure you
Yeah, I didn't get that.
that is it, because we recorded on your computer.
Yeah.
Oh, yeah.
No, but I was getting introduced.
Okay. I'm gonna be in my office.
Yeah, I will definitely come by. Yeah, is there someone that will take me? Drop by.